Hey everybody, let's go over a final analytical technique from chapter 4, section 4.5. So I'm working from my lecture 10 slides, okay? And this is a technique called combustion analysis, which is what it sounds like. You take a compound that you've created and you don't know the formula of it yet. You don't know the subscripts. You don't know how much of each mole of each element you have. And you send it off for what we call elemental analysis. Okay. And elemental analysis analyzes how much of each element is in your compound that you've synthesized, that you've made. And it basically relies on combustion. And we know that when we combust compounds that contain carbon, hydrogen, and perhaps oxygen, we always get the same two products out. What are the two products that we always make? We always make carbon dioxide and water. And so we're just going to focus on elemental analysis for those kinds of compounds containing carbon, hydrogen, and oxygen. When we combust and we produce water, the amount of hydrogen, the element hydrogen that is trapped, that is present in the water, had to come from the sample that you placed in this furnace, is what it's called, to begin with. That's the law of conservation of mass. The amount of hydrogen that you end with has to equal the amount of hydrogen that you began with. So we can also figure out how much carbon we had to begin with if we analyze how much carbon we got as a product in the compound CO2. So there's tubes that you can use. You trap the amount of water that's produced and you trap the amount of CO2 that is produced. And when you combust this product, you're not just burning it in air like we've been doing. You actually are combusting it in pure O2. So like I said, we're going to relate the mass of hydrogen that we had in the compound to begin with to the mass of water that we collected, and the mass of carbon in the sample to the mass of CO2 that we began with, that we ended with, sorry. And then if your compound also has oxygen in it, if the compound that you sent off has oxygen as well, we'll find the amount of oxygen through subtraction, okay? So I have an example, but I want you guys to, so let's see, this should be on your in-class, if you're following along with the in-class, I believe this is number 33. And I just want to remind you guys that if you look on your chapter 4 useful equations, and you look on the side that has the stoichiometry flowchart, I've put the problem-solving steps for combustion analysis here. So as we are working through this example, look at your steps and notice how we're following each of these steps, okay? So when we send a sample off, okay, in this example, we sent a 4.24 milligram sample that contains those three elements, carbon, hydrogen, and oxygen, all right? When this sample was combusted, it produced 6.21 milligrams of CO2 and 2.54 milligrams of water. First thing, and then I also told you in this problem that the actual molar mass, because we're going to end up finding the molecular formula, the actual molar mass of this compound is 60.06 grams per mole. So we're going to take the amount of CO2 and convert it to grams of carbon. And there's two ways that we can do this. We can set up a train track, which is actually what I believe the solution is on the slides. Yeah, on the slides, I solved this like a train track. If you go back and look at chapter 3, right, and we learned how to convert from grams of a compound to moles of the compound to moles of an element in the compound, then to grams of the element. Okay, that's what I'm going to do. We also learned in chapter 3 that you could use the percent composition of a compound to get the mass of an element. I'm actually going to work it that way. That's what I'm going to do. So you guys may prefer to always work it this way, and that's fine. Oh, maybe here. Okay. So if you're going to work it with mass percents, okay, which is the way I'm going to show it here in the video, then what you need to remember is that the percent carbon by mass in carbon dioxide is, and it's this number always, okay, 27.29%. Always, this is the percentage, 27.29% by mass. So if I have 6.21 milligrams of CO2, multiply that by the percent carbon by mass. That would be 27.29 grams of carbon for every 100, or sorry, I said grams, and it is, you can use grams, but you can also use milligrams for every 100 milligrams of CO2. Okay. And then you'll get the milligrams of carbon. I want milligrams in this problem because all of my numbers are in milligrams. Okay, I'm going to work with milligrams in this problem. So you should get 1.69 milligrams of carbon. This is what was in the sample that you sent for analysis. That's how many grams of carbon were in there. Next, convert water. So yeah, let me say milligrams to milligrams of hydrogen. And again, you can solve this using a train track, dimensional analysis, or you can use mass percents, which is what I'm showing here. The train track solution is on the slides. If you're going to do this way, the percent hydrogen by mass in water. Remember, how do you find these percent by masses? There's 2 hydrogens, so you would take the molar mass, 2.02, divided by the total molar mass, 18.02, times 100. That's how I got these percentages, okay? Percent by mass of hydrogen in water is always 11.21%. Again, that's always true. You don't have to solve that over and over again, okay? So math-wise, what are we doing? Amount of water, 2.54 milligrams. And if you just want to show me this way, you're just multiplying this by the percent, right? You take divided by 100, that moves that decimal. You're just multiplying it by the percent. Percent hydrogen by mass. You should get 0.285 milligrams of hydrogen. And again, this is what was in the sample. So the first question said, find the mass of each element. First part A said find the mass. Okay, well, we found the mass of carbon. We found the mass of hydrogen. And to get the mass of oxygen, we subtract. Take your sample size that you sent off and subtract how much of it is carbon and how much of it is hydrogen, and what's left over is oxygen, because it was only made of three things: carbon, hydrogen, and oxygen. That's, again, the law of conservation of mass. Okay. You're going to round that to the thing. I think you end up getting 2.27 milligrams of oxygen. Okay. So there you go. You found the masses of each thing. That's always the first step that you need to do, whether the question asks for that or not. You have to find these masses, because then now we're back to following our, from chapter 3, find the empirical formula. Okay. We're doing that same step, starting, this is the only new step, converting from CO2 to carbon and water to hydrogen. That's new. Everything else from here on out, finding the empirical formula. Convert milligrams of carbon to moles. Convert milligrams of hydrogen to moles. Convert milligrams of oxygen to moles. Okay. Divide by the smallest amount of moles. Get your empirical formula. To get the molecular formula, you had to be given the actual molar mass. Divide this by the empirical mass. Get your coefficient. Get your number, your multiple. There you go. Okay. So hopefully introducing this first part will help us work through some more examples. I believe I have another video in the pre-recorded lecture folder of me working through the next in-class example, which would be 34. Okay, so you might want to check that out, and we will work one together when we come back to class next time. Okay, thank you guys.